Unreal Engine, Unity, Godot! So many options, yet people are still creating their own Unreals. Hi, I'm Deriv'era, and I've personally written two engines, one based on OpenGL and another on DirectX 9, not to mention smaller 2D pixel movers. Unreal Engine enjoys to crash, sometimes for no apparent reason. Sometimes you need to do a lot to get just a simple result you can code and see in much less time, because you need to deal with massive amount of systems linked together that Unreal Engine offers you to cover all possible scenarios. Have you heard about YOLT physics? I tried using it 2 years ago with my OpenGL engine. Back when YOLT wasn't as popular, this physics library was constantly crashing my game under a specific scenario when raycasting hit a body that was later removed from the scene at the same frame. That issue pushed me towards my own physics system. Even though it was much simpler, at least it worked without crashing. Sometimes the saying if you want to do it good, do it yourself really holds the truth. When you build something yourself, it's simpler to understand and much easier to fix. The problem is that only a few people are willing to create their own solutions instead of relying on existing ones. Amount of time needed and intimidation of unknown sounds scary. Developing a game engine takes a lot of time, and the common opinion on social media encourages people to stick to existing solutions, but generalizations are bad. And I'd like to dive deeper with you into the reasons. First, let's explore what the game engine is, how it works, and how challenging and time-consuming it can be to develop its various components. To render polygons, you need 3 matrices and an understanding of how to display polygons using your chosen graphics API. Everything beyond that is just an enhancement. Matrix is just a 2-dimensional array, typically 4x4, and is a fundamental part of linear algebra, a subject taught in universities. I started learning about matrices on my own in school because I was already interested in graphics, so they are not very difficult to grasp. The 3 matrices you'll need are projection, view, and model. Projection determines perspective distortion, or the lack of it. Using this matrix, you can set the coordinate center to the middle of the screen, the top left corner, or any other point. For perspective, it allows you to adjust the viewing angle and set how far polygons remain visible. Model matrix handles transformation of objects in your scene. You will require it to move your 3D models or 2D sprites around. A single set of polygons can represent countless objects, and the model matrix positions, rotates, and scales them as needed. View matrix handles your camera. Camera can be represented as model matrix, but in the final equation, view model should be inverted. So the entire scene will be placed relative to your camera. In other words, you move not the camera, but the world around you with this matrix. When you multiply these 3 matrices together, you get the model view projection matrix. After multiplying it with each vertex of your mesh, you will get their positions on the screen surface, ready to be rendered. 3D graphics operates within fixed internal dimensions, and the MVP matrix transforms your vertices to fit within these dimensions, or not fit, in this case they are cut off. Once transformed, textured triangles are displayed at their positions. This is called rasterization. How this whole pipeline works depends on graphics API you're using. Modern APIs like DirectX and OpenGL use vertex shaders, which allow you to define how exactly screen positions for vertices are calculated. In a basic setup, the vertex shader receives the MVP matrix and multiplies the vertices with it. Pixel shader, also called fragment shader, handles the color of each pixel in the rendered triangle. There are different approaches to set up the process on different platforms. For example, the PSP SDK allows you to set up 3 separate matrices via commands, and they are multiplied internally. With OpenGL and DirectX, you must manually handle matrix multiplication. PSP uses a fixed function pipeline, meaning it has no shaders and 3 main matrices are integral. Modern OpenGL and DirectX require you to load 3D graphics and textures into the video card's memory or VRAM, while PSP allows rendering directly from RAM. Similarly, older versions of OpenGL had functions for drawing polygons by directly providing vertex and UV data as function arguments, without loading them into VRAM. However, this method is extremely slow. If you are new to working with matrices, you don't necessarily need to learn the underlying math. I use a library called GLM, which was created for OpenGL but can also work with DirectX with some adjustments. GLM includes all of these matrix operations optimized with x86 SSE where applicable. Despite all of the progress, there are still only 2 major methods of rendering: forward rendering and deferred rendering. Forward rendering requires to send all the data needed to render a polygon into a shader and process it in one go. It was the most commonly used method when shaders were simple or non-existent. Deferred method renders the scene into several buffers, storing information such as depths, normals, and material properties, without applying lighting or final colors. The final image is constructed using this data, and lighting is applied only at the end. This is highly optimized for complex lighting effects, but consumes more VRAM due to the multiple buffers. It's less common to see on mobile devices, but is preferred for PCs. Unreal Engine uses deferred rendering by default, as did my first serious attempt at a game engine with OpenGL 4.2. The main issue with forward rendering is overdraw. If a scene is rendered back to front, pixels at the back are fully calculated, only to be overwritten by closer pixels. With the complexity of modern pixel shaders, this is a performance killer. But Doom Eternal's engine is using forward rendering. Modern approach to forward rendering is first to render everything into depth buffer that stores how far each pixel is, without any color output. Then only the pixels matching the current depth buffer are rendered. That's how my DirectX 9 engine works, and I'm pretty satisfied with performance. The biggest drawback of deferred rendering is its inability to handle multiple transparent objects in the same buffer. It only stores information about solid objects, so after the solid pass, you still need to use forward rendering to draw transparent objects. I think DirectX 9 and 10 gave a significant boost to deferred rendering because they had limitations on the number of parameters you could pass to a shader. For complex scenes, you needed to send a lot of lighting data, including shadow textures to render a polygon. I personally faced this issue with DirectX 9, however, with modern technologies, these restrictions no longer exist. Both modern forward and deferred rendering have their place, and I can't say one is objectively better, they are just different approaches. I could talk a lot about graphics beyond these basics, for instance about PBR, reflections, global illumination, but let's have a stop here. My first implementation of rendering with OpenGL 4.2 took me about a month, with another month to polish it. The time required really depends on the level of graphics quality you aim to achieve. If you thought graphics rendering was a challenging topic, brace yourself for the next two subjects that still drive me crazy to this day: physics and UI. It took me a month to implement basic game physics, and I'm still far from satisfied with the results. I read a book called Game Engine Architecture by Jason Gregory and watched a presentation by Dick Gregorius, a Valve employee, that provided a lot of insights into Valve's approach to physics. I also did extensive googling and used ChatGPT to figure out specific functions I couldn't find anywhere in form of code. Of course, I then had to debug the errors that ChatGPT introduced. Some portions of physics I was able to find only in the form of mathematical formulas I didn't understand, including Jason's book on game physics. That's the area where I felt the most lack of good knowledge of math, and only here I finally engraved into my brain what are dot product and cross product. Detecting the fact of collisions is one part of the problem. You also need to resolve collisions based on the center of mass, apply torque, and manage acceleration. There are a lot to handle. When it works, it's incredibly satisfying to see. I felt joy, but most of the time it didn't work, and I spent days trying to figure out why. The worst challenge was handling polygon cutting, which is required to detect surface-to-surface collisions, so your box can be still while resting on a big polygonal mesh. So you need to ask yourself about your goals in life in general, and if you are ready to approach this. An alternative to writing your own physics system is using existing solutions like Yolt physics. If you're eager to focus on graphics rendering but want to avoid writing your own physics and collisions, Yolt might be the right choice. Yolt is constantly updated and, in my opinion, is the best game physics you can get for free. UI development can seem straightforward until you attempt to implement a general-purpose UI system. If your goal is a few buttons and maybe a couple of switches, you can likely avoid creating a system at all. However, building a fully featured UI with dynamic scroll bars, automatic resizing based on screen resolution, icon and text arrangement, and the flexibility to make something akin to a web browser is a significant challenge. And to make good options menu or map editor, you will require a lot of this. The main issue lies in the dependency of lower elements in the UI tree on higher elements and vice versa. Flexible top elements will require to know sizes of children elements, but flexible children elements will require to know the size of parent element. UI tree is not just a tree, it often requires portals or systems to align and interact between elements dynamically. It's like dealing with the four-dimensional tree, as the relationship between elements are complex. I created a UI system capable of building sophisticated tools like map editors and notepads with models, buttons, and more. It took as much time to develop as my physics engine. Half of that time was spent debugging or discovering that the system needed additional functionality, requiring significant rewrites. Unlike graphics or physics systems, where subsystems and functions often just work after proper implementation and testing, UI systems tend to be more monolithic, with changes often affecting the entire structure. Later, when I built my DirectX 9 engine, I rewrote the original UI system again. Despite the revisions, it still has numerous limitations and unresolved issues, with much more work left to be done. And really, I don't even have any specific UI libraries to recommend, so I really hope you will only have simple buttons. But I believe everyone appreciates a game with plenty of options and settings, including accessibility features like adjustable font sizes or color-blind friendly shaders. Implementation of sound, on the other hand, is surprisingly straightforward. You'll need two buffers. While one is playing through your speakers, the other gets updated. This can even be done in the same thread as the main game logic, after rendering step, or in a separate thread. To mix multiple sounds, simply add their samples and ensure they share the same sampling frequency. This will simplify your life. Sampling frequency refers to the number of samples captured per second. For 3D sound in a scene, you'll need to calculate the dot product of the camera's side direction and the vector from the camera to the sound source to correctly position the volume between the left and right speakers. That's the basic setup, of course. But as with any part of a game engine, there is endless room for improvement depending on your goals. And yes, I wrote my own sound mixer for a reason. Initially I implemented sound using OpenAL, but I quickly discovered that just because it works for your setup, doesn't mean it will work for others. With OpenAL, your game might encounter sound issues when shipped to other people. The stream of samples you provide to SDL2 is just more reliable. Or you can pay for FMOD license. FMOD is commercial industry standard for sound. For OS-related tasks like keyboard and mouse input or window management, you can either directly use the OS API, which has plenty of guides for both Windows and Linux, or rely on a library like SDL2. SDL2 simplifies these interfaces and makes your project cross-platform by default. Windows API is horrible. Linux API feels as some alien technology that just works most of the time. So if you have watched this far and still feel like writing your own engine, let's continue with comparisons. Experience. Writing a game with an existing engine and your own offers different knowledge. If your goal is to improve as an Unreal Engine developer, I recommend spending as much time as possible with Unreal Engine. The big chance is that your own game engine won't provide much relevant knowledge if you didn't reach proficiency with the game engine of your choice. It's possible to create 100 games without ever delving into how engine works under the hood. If you believe low-level development will be an advantage for you, I'd argue it's only worth pursuing if you already know an existing engine on top level inside out and want to explore deeper concepts. Especially if you are interested in something more experimental, like 4-dimensional worlds or P not being 3.14. For beginners in programming, I wouldn't advise to drop the idea of writing your own engine. Instead, I believe you should carefully analyze your end goal. Ask yourself two questions: what you want to create? The latter is simple but particularly important. Building your own engine can be an incredibly valuable learning experience. Starting with a 2D game that avoids existing engines, like a top-down shooter with sphere collisions, can teach you a lot. I've worked on such games long ago too, inspired by Notrium and Crimson Land. If you are building a portfolio to land a job as a game developer, projects made with an established engine will likely carry more weight on your resume. While building your own engine can give you theoretical knowledge, employers tend to be more interested in practical experience. The number and quality of completed games demonstrate your skills and decision-making far better. Managers have no idea how the fuck these things work anyway, and in my experience not many people you meet in the interviews will even understand the significance of such projects. But with such knowledge you might have fun interviewing the interviewer on 3D subject. And the last but not least, I think it's obvious that challenging tasks just improve your skills in general. Retro. I'm really happy to see more and more developers creating games for retro hardware, like the Commodore 64, Game Boy and Sega Mega Drive. There is something special about these projects. They are not just retro in style, but retro in their heart, fully embracing the limitations of the original hardware. For me, the feeling a product evokes and where it belongs is the same important as the product itself. Making a game with Unity misses the constraints of the era. Tools like Unity enhance certain aspects of game development with the utilities they provide. Unity or Unreal offer modern workflows for tasks like level creation, where you can simply place elements into a scene. But back in the days, level design tools were much harder to come by, and they provided much less functionality with heavy optimization in mind. Take Painkiller for example. It had empty rooms and strange unused spaces just because creators had very limited level design tools. Since the game used its own engine, they had to work within its constraints. Documentaries about games like this often contain notes about the struggles of developers faced without the tools we now take for granted. Another example is Silent Hill 2. Retro technologies like DirectX 9 push you to compromise on amount of bonds and characters due to limited amount of shader parameters. All of this affects the feel of the game. These kinds of problems simply don't exist when using modern engines, but retro technologies force creativity in ways that modern tools don't, and I think it's valuable. Don't get me wrong, I don't want to sound mean to developers who create retro-styled games with Unity and Godot. Retro-styled games are entirely valid and often amazing. Time. It might sound obvious that existing game engines require less time to make an actual game, but that's not entirely true. Certain types of games can actually be slower to make with engines like Unity compared to using C++, when all you need is something simple to render sprites. Experience plays a big role here. When comparing development time, it's important to consider the same investment of time in learning and working with tools. For instance, I can develop certain indie-style games much faster using C++ and my own technologies than with Unity, which I've never used before, or even Unreal, which I have used only for a few demos. What types of games do I think are easier to create with just sprite rendering and no extras? Turn-based games are one example. Writing all the state management directly in C++ feels cleaner and more straightforward to me than doing the same in Unreal Engine. In general, games that don't require a map or scene editor might be easier to develop using plain code and a simple rendering engine. However, as soon as you need to organize a level, editors become incredibly helpful. There is a huge difference between making a space station game where you need to combine rooms, doors and other elements versus an open space game where stations can be placed randomly, eliminating the need for a map editor entirely. Of course you can write your own map editor, something I've done before, but that's also time consuming even if the editor shares a lot of code with the game itself. On the upside, having your own editor means you can share it with players, enabling them to create custom maps, a big bonus for player engagement. So again, it heavily depends on your specific project. Hardware support. With your own engine, it's obvious that you will have full control over which hardware you want to support. If you want your game to run natively on platforms like PSP, PS2 or Sega Saturn, creating your own engine is probably the only option. When you tell people that your game supports older hardware in addition to PC, it tends to generate more excitement. It's a feature that can be leveraged to promote your game and make it to stand out. Community. When selecting a platform to develop with, the community around it is incredibly important. For example, when Godot wasn't as popular, the lack of community means the Godot team didn't get as much testing or feedback. And if you are writing your own engine, you'll likely find yourself in a community of one person. You can try to connect with others who enjoy low-level programming, but communities like those around Godot or Unreal are much larger, more organized, and more active than any group you are likely to find for custom engine development. In many cases, you can't rely on tools like ChatGPT for help if you allow LLMs in your life. ChatGPT is good for solving surface-level problems, but many of its solutions on deeper topics better not to follow. Stack Overflow can sometimes help, so it's slow to get answers, and I wouldn't exactly call it a community. It's more like a collection of developers you'll never interact with again after you issue is resolved. What I'm trying to say is, with custom engine development, you should be prepared to be left alone. For difficult topics like advanced physics or implementing Lumen-style lighting, you may find no specialist readily available to help. Most people write articles or make videos, like me, rather than engage in direct communication. With Godot, however, I'm more than confident you'll get support when you need it. In terms of community, I honestly think Godot is one of the best. Coolness! I honestly think that if you go to a community of regular gamers and tell them you are making games with Unreal, they'll be excited. Unreal is something everyone recognizes and most people associate it with a lot of impressive titles. That's the main reason. On the other hand, if you tell game developers you are using Unreal, they'll probably just nod and say, okay, it's a great tool for game development, but it's not exactly out of the ordinary. Now, if you tell regular gamers that you are writing your own engine, they'll probably be confused, wondering why, how, and even what a game engine actually is. Developers, meanwhile, might be even more confused. Many argue that game developers should use existing engines to focus on creating games rather than reinventing the wheel. Still, they'll think you're cool. I honestly believe there isn't a developer out there who wouldn't find a custom rendering system producing high-quality visuals impressive. Also, maybe I'm completely off track when it comes to measuring what's cool. And if you think people don't care about which game uses which engine, here is a screenshot from a discussion about Faster Than Light. When people ask you why, it's actually a good sign. It means they're curious and interested. The worst response is when they don't ask anything and just say okay. Even hate towards your game is better than just okay. Your personal feelings. I think you should listen to your heart, especially if you are still unsure. If your heart is telling you to try this path, there is no harm in trying. At every step of engine development you'll gain knowledge, and if you enjoy the process, well, that's a bonus. In conclusion, I want to say that I personally don't regret spending so much time on what I've created. My projects are the only reason I'm able to give you these insights and share my personal experiences. Despite the availability of books and many YouTube videos, this topic is still not easily approachable. It's not something you can learn effortlessly because there is no structured knowledge out there. Even the complexity of books is questionable. For instance, books on game physics often assume you have university-level math skills and fail to offer simple, clear explanations on the most complex topics. I really don't want games to look the same. Unreal, Unity, and Godot each have different rendering pipelines and approaches to development, and Godot feels like a breath of fresh air simply because games built with it have their own unique feel, at least I believe so. More engines and more limitations will lead to more diverse experiences. Limitations are actually great because they push your imagination to find ways to overcome them and create enjoyable games. For instance, Playdate Handheld is popular for a reason. When a game is made using a custom engine, it already piques my interest because of how rare the phenomenon is and the level of technical knowledge the developer must have. Fallout 4 doesn't feel like a game made with Unreal or Unity. It feels different because it runs on a custom engine. And I think that's a good thing. If you believe that Bethesda switching to Unreal would make their games run better, I would argue against it. Without top-tier developers, that wouldn't happen. In fact, things might even get worse for at least a few years. A great example of a custom engine is Modern Doom. It's especially surprising because ID Software belongs to ZeniMax, the owner of Bethesda. Reading about Doom's engine and how it works feels magical. In many ways, it's genius, showcasing what developers with deep knowledge and expertise can achieve even without Carmack. Knowledge and better management are the only things that can save the modern AAA industry. Despite having so many experienced developers and talented artists, management sucks. There are creators on one side and managers on the other who force creators to follow their whims by instilling fear of being fired. Nowadays, managers rely on generative AI as a tool to smooth over their own mistakes, but they themselves are the reason of games' bloated budgets and failing live service projects. If they want AI in game industry so much, they should replace managers with AI, to have clear goals and understanding of both players and artists. And the AAA industry could start making great games again, because it already has incredible artists and programmers. Problem is not among them. Above these creative people sit individuals detached from both players and the creators, filled with nothing but buzzwords and empty promises, a poison to the industry. CEOs of public companies which depend on investors should also be replaced with mascots. CEOs are pointless and exist solely to appease investors. Their vision is failing all the time for consumers. Just look at Metaverse and NFT games. Just imagine the return of mascots. Just picture Pepsi Man saving us all from dehydration in an Astro Bot style game. If you can predict what these managers and CEOs are looking for, you can probably land a nice job in the gaming industry. It works this way, not based on who has the best skills. In many companies, management is circle jerking each other and expect creators to do it for them as well. Once I worked in one office for one company, we had strict rules about light bulbs in our office. They enforced strict rules about the spectrum or warmth of the light. Out of corporate design, no one cared about health. Meanwhile, our project manager was so depressed he could barely force himself to come to work, so he worked on full remote, ignoring rules. I didn't even know his face. He wasn't able to force himself to retire for several months, even if wanted. But at some point he succeeded, and only after that we found out that our work as devs was misled. Wrong design was approved that is physically impossible to implement, but light bulbs, don't mess with light bulbs. HR department will eat you alive. In other office, HR hated me for drinking too much yogurt from the public fridge. You can have a salary of several thousand euros, but yogurt is limited. At the same time, we were forced to work in the office on painfully slow Dell laptops riddled with corporate spyware. Copy-pasting code in the IDE lagged. Just imagine the scale. After numerous complaints about various issues, the company decided to fire the manager of our department, the one person who actually tried to address our concerns and improve things. Probably he tried too much. I can tell you more stories, but the point I'm trying to make is that what you decide to do, including game engine development, should be based on your needs and goals. Of course, it's up to you. This is just my opinion, some person on the internet. These examples show that skills alone don't always translate into the accomplishments you might expect, like getting a job, because initial conditions are absurd. You need to convince people that they need you. The knowledge itself is not so important. That's the reality, and I hope my videos help change it even a little. Thank you for listening. I appreciate your likes and subscriptions. As well, I appreciate your dislikes too. I observe them with no idea about what the silent people didn't like because they don't leave comments. Wishing you luck and great games both in playing and creating, or at least I hope you can enjoy the bad ones too. Bye.